All right, so the next thing to look at is to look a little bit at how the fields look inside of a waveguide as well as what happens with the power transmitted down a waveguide. So this is and we'll focus mostly on the TE10 mode while also talking about what happens when you go to higher order modes. So first of all, thinking about the field distribution, where the peak is located and what the actual intensity is of the peak is important because you don't want to break down the dielectric in the waveguide, which can be a problem with really high fields. So for example, here is the distribution. If this is the cross section of the waveguide, and we're looking at the Y component of the electric field, you can see that it looks like this. And then if we just define that as some value E sub 0, which would be the peak in time and space, that can be expressed as this omega mu A, which is the waveguide dimension, over pi, and C, which is a constant. So you can, of course, solve for the constant C based on the peak intensity of, or the maximum intensity of the electromagnetic field in space and time. So ultimately, you could basically just replace most of this whole thing with E sub 0. So the power in the waveguide can be found excuse me, by taking E cross H star and dotting that with Z. And so in doing that, we can substitute in terms of this peak field intensity E naught, we can substitute for C in the electric field E. And then obviously taking E cross H brings in eta. And so when we do all of this and make our appropriate substitutions for eta, the impedance, and look at it in terms of the amplitude of the electric field, we get this expression here for the peak power. And that'll be 2 times the average power. So the average power would have our factor of 1/2 here. So if we look then at this expression, we can see that the peak power is a function of the peak electromagnetic field, the guide dimensions A and B, the impedance eta, the wavelength, and then here's the guide dimension A repeated again in the square root sign. All right, so let's talk a little bit about attenuation in waveguides. So attenuation in waveguides occurs for 3 possible reasons. The first 2 reasons concern losses, and the third reason concerns waves that won't propagate because they don't meet the cutoff frequency and guide parameter guidelines. So first of all, we're going to have losses in the conducting walls of the waveguide. Because remember, in the boundary conditions on H, the tangential H field is discontinuous by the surface current. So because we do have a boundary and it is a metal and the current can flow, we are going to have surface currents on the walls of the waveguide. And so anytime we have currents and we have a non-perfect conductor, we're going to have resistive losses in those conducting walls. Secondly, we'll have losses in the dielectric medium between the waveguide walls because dielectric either has non-zero conductivity sigma, or we can also think of that as a complex permittivity, where the permittivity is epsilon prime minus j epsilon double prime. And remembering here that these factors, dielectrics tend to get more lossy as frequencies get higher. So loss in a dielectric is proportional to frequency, and this tends to be more of a problem when we do get to the waveguide, to the microwave type frequencies. And then finally, we also get attenuation of a wave if it's an evanescent wave, meaning it's a wave that doesn't meet the frequency criteria to propagate in a waveguide of specific dimensions. So this frequency would be below cutoff. So we'll still get some propagation, but it will die off relatively quickly. Okay, so the loss due to surface currents is the dominant loss mechanism, and here's an example of a rectangular waveguide, dimensions A and B, and an illustration of what the surface currents look like in the TE10 mode. So you can see they're distributed as such in the surface of the waveguide material. So once again, the average power in the waveguide for the TE10 mode we can find by integrating 1/2 the real part of E cross H. So this is like 1/2 VI star real part. So this is finding the power that's actually dissipated. very analogous to finding the power P in an AC circuit, except here we're using E and H and not V and I. And then we dot that with C, the direction of propagation, and do the surface integral over dx and dy. So we plug in the expressions for the E field in the y direction and the H field in the x direction, and we'll do that for t equals 0. So what we get is the following integral, and so we pull out all these constants, and we're actually integrating over sine squared. When we do that, we get a squared over 2 by making the 1/2 minus 1/2 sine 2 theta substitution. So you can see the result for the average power in the waveguide. Now the power loss at the walls, we're actually finding I squared R losses. And so in this case, because we have a field and it's non-uniformly distributed, rather than finding I squared, we're finding the integral of J squared. So we have the integral from 0 to A, which is the top wall, the A dimension of the surface current at y equals 0, and that's squared, and then it's times R, and so we have basically the surface current in the x direction and the surface current along the x direction and the surface current along the z direction, taking this obviously for a unit length, and then R is the surface resistivity of the guide. And so when that integration is done, plugging in for surface current J, J surface in the x direction and surface current in the z direction, we then get the following expression for the power loss in the walls in the y direction. So then we will double that so that we have two of them, one at 0 and one at B. Then we do the same thing for the power loss per unit length on the surfaces in X, the one at X equals 0 and the one at X equal A. Once again, integrating 1/2. In this case, we only have a y component of J. So we square that times RS. We substitute for JY, and in the end, the integral comes out to yield this result. The surface resistance is given by the square root of omega mu over 2 sigma. So that then gives us power loss in the walls, in all 4 walls. And so once again, we'd have to double this in order to get both so you see you have 2 times the power loss at x equals 0 and 2 times the power loss at y equals 0. All right, so if we add those together, we get the following expression, and that's defined as the power loss. So alpha, which is the attenuation constant due to losses in the conducting wall, is defined as the power loss over 2 times the power transmitted. So after some substitution from the previous average power that we solved for and the power loss that we just solved for, we come up with this expression for alpha, the attenuation constant due to losses in the walls. And we can make some substitutions in order to find, this is for the 1-0 mode, but if we wanted to find for the random MN mode, we'd make some substitutions and we get this expression here, equation C32. So that's how to get the attenuation factor due to resistive losses in the walls. In the next lecture, we'll look at other loss factors, and then we'll also look at how this impacts the field.